Okay, we're going to take a look at what you learned in your lab. You took a spring and you stretched it. To stretch it a certain displacement, you had to apply a certain force to it. And if you stretched it a little bit, you applied probably a smaller force, and then that kind of correlates to the fact that you have a small amount of energy stored in the spring. If you stretched it even further, the amount of energy stored in that spring elastically increased. And if you stretched it even further, that amount of energy that was stored in that spring increased to an even greater amount. We're using pie charts to show the amount of energy stored as we did before. And in this particular time, we have the pie charts actually getting bigger to accommodate the growing or the increasing amount of energy stored elastically. But another thing we do from our graphs is we write our equation. So our equation from the graph, again, y equals mx plus b is our format. Instead of y here, we have force. Instead of our slope, or m, a generic term, the slope on this graph actually stands for something called the spring constant, abbreviated by the letter K. So F equals K, then displacement, our x value is displacement, so not x, but delta x, and our y-intercept is 0. So for us right now, we have F equals K times delta X, or the force equals the spring constant times the displacement. But really, what is the spring constant? To describe that a little bit more, we can look at, it's really considered how stretchy a spring is. Or more officially defined as the force required to stretch a spring a certain displacement. And typically, the easier to stretch you have a small k, right? A smaller force required to stretch at a certain displacement, and the harder to stretch a large k, a relatively large k value. That applies to this question up in the top right corner. It says, what is the spring constant? So that is looking for the slope. Based on that, I can pick my 2 points, 0 meters, 0 newtons, so 0 displacement with 0 force, and 4 meters of stretch with 6 newtons. Looking for the slope, 6 newtons divided by 4 meters, or 6 minus 0 divided by 4 minus 0, is equal to 1.5 newtons per meter. That is a relatively low spring constant in our general terms when we look at springs that we deal with in class. Additionally, besides just our slope and our equation from our line, there's usually one other part of the graph that helps us identify some physical quantity, and that just happens to be the area under the graph again. Just like we did a couple units ago, the area under the graph now has meaning. So if I'm looking at how much energy I have in a spring, that happens to correlate nice to, and actually be defined as the area under the graph. So if I have the energy or the spring stretched the full amount, I see a great deal of energy here, and the area under the graph is a large quantity as well. If I were to compare this to the orange kind of pie chart from our middle example, perhaps that correlates to the area under that portion. And even more so if I'm looking at the smallest pie chart here, the smallest displacement, that would be maybe perhaps even a smaller area looking at that displacement. But as usual, we want to write an equation for these sorts of things so we can use it again later in a different scenario without having to graph each time. So the area under the graph is equal to the energy stored. For our particular case, the area is a triangle, so equals to 1/2 times base times height. And this is the energy stored elastically is equal to 1/2 times the base, which is displacement, times our height, which is force. Because we might not necessarily know how much force we're applying, but it's easier to measure the displacement, we can remember back to our equation from right up above and say to ourselves, well, if we want to replace force, we can substitute in this K delta X, or spring constant times the displacement. So our elastically stored energy is equal to 1/2 times displacement times K times displacement. And as usual, we'd want to simplify that. And the elastically stored energy is equal to 1/2 times K delta X squared. This little graph over here puts that to use a little bit. It says how far does the spring need to be stretched, so which displacement, to store 8 joules of energy elastically. As you recall, joules is a unit for energy, and in this part we're just looking for where the area is equal to 8 joules. This is a little bit trickier. It's an easier problem. It wouldn't be given to you for something with such a decimal. That would be hard to figure out. But graphically we can kind of see that at a displacement of 4, 1/2 times base times height, 1/2 times 4 meters times 4 newtons is equal to 8 Newton meters. So that is the area that would get you 8 joules, the displacement of 4 meters. Okay, that's all about energy stored elastically, but we've talked about different energy storage modes, and we should probably come up with an equation for those as well. So in our case, if we're looking at the energy stored gravitationally, really we could look at the force of gravity on an object at different heights above the surface. And since the force of gravity doesn't change, we get this horizontal line kind of showing no relationship, or at least no change or no correlation to the height. Remember that the area under the graph represents the energy stored. So now we can come up with another equation for that. So area in this case is equal to base times height, because we have a rectangle, and we're looking at the area stored gravitationally. The base of our rectangle, this is where it's kind of funny, the base of the rectangle right here is height. And the height of our rectangle is the force, and in particular, our force of gravity. As we generally do, we probably have something we can substitute in. So thinking back to our equations that we know, force of gravity is equal to 9.8 newtons per kilogram times mass. So we can substitute in 9.8 newtons per kilogram times mass for Fg. Commonly we're given masses in science instead of forces to accommodate if you were on a different planet. So substituting that in, Eg, or energy stored gravitationally, is equal to the height times 9.8 newtons per kilogram times mass. And that's pretty much our equation. A couple of differences. Height might be listed as y or delta y to talk about the vertical displacement or vertical position of an object. And that 9.8 is sometimes referred to as g, assuming we're on Earth, the gravitational force field. Right? If you went to the moon, you would have a different value or a different amount of energy stored gravitationally. Okay, gravitationally stored energy and elastically stored energy are taken care of. But our last one, we have kinetically stored energy. For this one, we can take a look at, again, if we apply a force, and in this case, it's going to be a net force that we're applying to something to get it to move a displacement, we can see that that net force causes the same displacement each time. This energy, again, is represented by the area under the graph. So we can look back to area equals base times height. And on that note, energy stored kinetically is equal to displacement times our net force, our height. We know that net force is equal to mass times acceleration, your favorite equation from last unit. And if we want to substitute in for our net force, again, something we don't generally measure, you can substitute in mass times acceleration. So energy stored kinetically is equal to displacement times mass times acceleration. I'm going to rearrange that for a very specific reason. So energy stored kinetically is equal to mass times acceleration times displacement. Again, the property of multiplication doesn't matter what order you do it in. And I did that, if you can see. Now, looking at our kinematic equations, Vf squared is equal to 2a delta x plus Vi squared. Assuming that our initial velocity was 0, that drops that term, and we're left with Vf squared equals 2a delta x. Well, as we're in the mood for substituting, if I want to substitute in something for a delta x, I have to solve for a delta x. That would require me to divide both sides by 2. So Vf squared divided by 2 equals a delta x. I can then plug in Vf squared over 2 for a delta x. That gives me energy stored kinetically is equal to mass times Vf squared over 2. Rearranging this, I don't usually like 2 as a fraction on the bottom, but more as a coefficient. So energy stored kinetically equals 1/2 times mass times velocity squared. We usually drop that final velocity. And that is the equation for energy stored kinetically. We can summarize it down below. Elastically stored energy is equal to 1/2 k delta x squared. Gravitationally stored energy is equal to height times 9.8 newtons per kilogram times mass. And kinetically stored energy is equal to 1/2 mv squared. One more thing to talk about is the units that come along with this. The units for energy are, or the SI units, are joules. It's abbreviated by the letter J. Looking at that, that's also equal to Newton meters. And you can kind of see that from our original equation for energy stored elastically, or even kind of over here, height times newtons per kilogram times a mass, or kilograms given you that, would be a meter times a newton. Additionally, you might be thinking, how does kinetically stored energy, how does a mass times a velocity squared get you a newton meter? And if you remember back to, right, this would get you kilograms times meters squared over seconds squared. If we remember back to what a Newton is really equal to, a Newton is equal to kilograms times meter over second squared. So therefore, a kilogram meter squared over second squared would be equal to a Newton meter. You have one extra meter in that unit. Okay. On the back side, you are going to look at how to use these equations to help you with solving problems. Okay, so using these equations that we derived on the front side can kind of easily be applied to our bar charts that we've been filling out. So the first question, or before the first question, I guess it says, what is the initial energy of the ball? Second is asking about the velocity at point B, and the third is asking about the height at point C. But before we do that, it's probably best to fill out our bar chart. Our bar charts, again, would show the conservation of energy throughout the different positions in time. So at the first part, we could look not to forget to define our system. Our system would be the ball, the earth, the track that's on, and the energy at point A. It talks about having zero velocity, it has a height, it has a mass, so the only amount of energy that it has stored is gravitationally. Then at position B, now it has a height of 0, so no energy stored gravitationally, but it is moving, so therefore you would have all of that energy stored kinetically. And assumed, I'm kind of assuming at this point that this is a frictionless ramp. Then at position C, it goes up a little bit of a ramp. It has a velocity still, but it also has a height. So I don't know relative how much each one is. You know, it doesn't give me a specific height, and it didn't give me a velocity here. So just for sake of knowing, I know that it's moving and has some height. I'm going to give it about half in both the energy stored kinetically and energy stored gravitationally. But notice the energy at position A is equal to the energy at position B, which is equal to the total energy at position C. And you can kind of write that out like EG is equal to EK, which is equal to EK plus EG. Now that might look kind of funny. We might want to add in something like EG at position A is equal to EK at position B, which is equal to EK at position C plus EG at position C. So just kind of getting that idea in our head. All right, it's asking what is the initial energy of the ball? Initially at position A, all of our energy is stored gravitationally. So we'd want to use our gravitationally stored energy equation. So height times 9.8 newtons per kilogram times mass. And our height is given to us as 1.25 meters. 9.8 newtons per kilogram is for our gravitational force field on Earth, and the mass of the ball is given as 1 kilogram over here. If I solve that, the energy stored gravitationally at point A is equal to 12.25 Newton meters. Or we could rewrite with our other unit, 12.25 joules. Okay, so hopefully that wasn't too bad. But energy is not usually used just to find out how much, but to find out information about the object along a certain path. So for instance, question B asks, what is the velocity of the ball at point B? We know that the energy stored gravitationally at point A is equal to the energy stored kinetically at point B. So we can kind of write our own equation for this to figure out the velocity. That would be equal to the energy at point A is 12.25 joules, and energy stored kinetically is equal to 1/2 mv squared from above. So I'm just substituting this into our equation. We can come down and fill out what else we know. 1/2 times the mass of our ball, which is still 1 kilogram, times the velocity squared. To solve for this, we would have to multiply 1/2 times 1, which is 1/2, and then divide, or really multiply both sides by 2. So multiplying both sides by 2 gets us to 24.5 joules per kilogram, because we divided by that 1/2, or sorry, we multiplied by the 2 to kind of get rid of that, is equal to velocity squared. We aren't done yet because it's velocity squared. We need to take the square root, and the square root of 24.5 is equal to 4.95. And then knowing that we're looking for velocity, we know our unit is in meters per second. If you're a little confused on that, you can kind of think of that side note. A joule per kilogram is really equal to a newton meter per kilogram. And a newton was really equal to a kilogram meter per second squared. So then divide by kilograms and multiply that by the extra meter. The kilograms cancel. You're left with meters squared over seconds squared, and we took the square root of that. That leaves you with meters over seconds. So that is for that one. Part C is asking for what is the height of the ball at point C. So to solve for that, there sometimes are a couple ways to do that. We can't necessarily know that these are half of each other. So we really better write out an equation that shows that these two added together equals either the energy stored at position B or the energy stored at position A. I'm partial to A since we did that in part A, so the energy stored gravitationally in part A is equal to the energy stored kinetically in part C plus the energy stored gravitationally in part C. We again know that this was 12.25 joules. And then we have to kind of plug in our equations so we can further solve. So the energy stored kinetically at part C will be 1/2 mv squared. And that's the velocity at part C. You usually don't have to abbreviate, but just kind of to make a point. Plus the height times 9.8 newtons per kilogram times the mass. We know that the mass of the ball is 1 kilogram, so 1/2 times 1 kilogram times the velocity at point C, which is given as 3.54 meters per second, and that's quantity squared, plus height, again what we're looking for, times 9.8 newtons per kilogram times the mass of 1 kilogram. Coming down with that, 12.25 joules is equal to 6.27 kilograms meters squared over seconds squared, plus the height times 1, so 1 kilogram times 9.8 newtons per kilogram would be 9.8 newtons. The kilograms cancels. We would subtract over 6.27 from 12.25 and then divide by 9.8 to solve for H. And when you do that, H comes out to 0.61 meters. You kind of can see that. So 0.61 meters is the height right there. Okay, why don't you pause the video and try the second one on your own and then check your answer. Either scroll through the video to the end to see the answers or listen to the explanation. It's up to you. All right. Okay, ready for number 2? It says a 76.5 kilogram circus performer jumps off a platform that is 10 meters high onto a large trampoline. He then bounces back off the trampoline to an unknown height. The trampoline has a spring constant like our earlier page, of 900 newtons per meter and stretches a distance of 2.89 meters when the performer lands on it. So again, a bar chart would probably be a good idea to solve this before so we can understand what equations we have to make up. My system is probably going to be the person, the earth, the trampoline, the air, whatever you'd like to include in there. Up at position A, he has no velocity but a height of 10, so I would say that all of his energy is stored gravitationally. I put 5 bars up there for that. At position B, he's at the ground, and they even specify that the height is 0. And he's at a velocity of 0. So it's right at that point where he's at that maximum stretch. So all of this energy has to be transformed into elastically stored energy. But knowing that at position C, his final height is not as high as his initial height, that means that some energy was probably dissipated as he hit the trampoline, whether that was through it warming up or through sound. He probably had some amount of energy dissipated, which leaves only, if I had 5 here, minus 2, which would leave me 3 bars of energy stored elastically. Again, this number did not have to be 2. You could have had that be 1 and this be 4, depending upon what you chose to start with. This is for a qualitative way to help us write our equations. At position C, it then gives us a final velocity of 0, so no energy is stored kinetically, but it's asking us some unknown height. Our dissipated energy we could not get back. That could not help us go or convert into energy stored gravitationally, so that still is left there, and all of that energy stored elastically now is energy stored gravitationally. That's what the trampoline was used for. So looking at this point, we can say that EG at position A is equal to EEL at position B plus E dissipated at position B, which is equal to EG at position C plus E dissipated, and that's really at position B or C for our purposes. So it says how much energy is dissipated throughout this process. You can pick whichever one we have enough information for. So we know the initial height is 10 meters, so that's a clue that we know how much energy, or we can calculate how much energy is stored at position A. And now we have our choice between these two. Because we don't know the height at position C, we can't calculate this unknown energy, so we can't calculate the dissipated energy. We do know the spring constant and the amount that the spring was stretched at position B, so that seems to be the only way we can finish this problem. Plugging in our known values. Our mass of our height times 9.8 newtons per kilogram times mass is equal to 1/2 K delta X squared plus our dissipated energy. We don't have an equation for that because it happens in so many different ways. Plugging in our values, his height is 10 meters at position A times 9.8 newtons per kilogram times the mass of 76.5 kilograms. That's equal to 1/2 times our spring constant of 900 newtons per meter, then times our displacement of 2.89 meters, but that's the quantity squared, plus E dissipated, energy stored, or energy that was dissipated. 10 times 9.8 times 76.5 ends up being a value of 7,497 joules. And that is equal to our value of 1/2 900 times 900 times 2.89 squared. That is equal to 3,758.45 joules, and then plus E dissipated. To solve for E dissipated, or the energy that was dissipated, we'd have to subtract over this 3,758.45 from our other side, and that gets us an answer of 3,738.56 joules. So this number is about 3,738.56, and this value is about 3,758.45. So those actually were very close to each other. If I were to go back and correct my bar chart, I would probably put them a little bit closer, like 2.5 and 2.5 bars. But again, this bar chart is to really help us see the process, not to be perfect in the exact ratios. And if we looked even further back, this position A was 7,497 joules, so it was represented by that bar chart height. Okay, for question B, it's asking what is the height, or the final height of after the performer's bounce. So what's his height right here? That's referring to position C. So I would probably again think, well, I know position A is equal to my total at position C. We can pick any set of these equations to kind of mix up. So EG at position A, the energy stored gravitationally, would be equal to the energy stored gravitationally at position C plus the energy that was dissipated. We know from above that our energy stored gravitationally at position A was 7,497 joules. You could go through and recalculate that with H times 9.8 times mass, or you can just plug that in, is equal to our height times 9.8 newtons per kilogram times our mass, plus the energy that was dissipated, which is again a value we calculated right in the problem above. So 3,738.56 joules. We can plug in our other values that we know, which would be the height we're looking for, but we have 9.8 newtons per kilogram, and the mass of the circus performer is 76.5 kilograms. Add this to 3,738.56 joules that was dissipated. We end up getting a value. Subtracting this over, you can have 3,758.45 joules is equal to H times 9.8 newtons per kilogram times 76.5 kilograms. Divide over both sides by 76.5 and 9.8. You get a height of 5.01 meters. Now, a side note to this is you could have also approached this a little differently. And if you realize that your elastically stored energy was equal to your gravitationally stored energy based on the fact that the dissipated energy was the same, you could have also said elastically stored energy at point B is equal to gravitationally stored energy at point C, and solved that way. Again, putting this number 3,758.45 equal to our H times 9.8 times 76.5. It's just the same concepts. You're still using the conservation of energy to solve for that. All right, enjoy practicing this on your packet.